This model where we have the rate of change is proportional to the amount is good not just for growth but also for decay. So it works for growing populations or growing money with interest, but it also works in a situation like this. Imagine that we have detention in our class and the teacher doesn't tell us how long we're going to have to stay. So the teacher just says, well, after class, every minute you can flip a coin, and if you get heads, you can leave, and if you don't get heads, you're going to have to stay. And then you stay another minute, and then you get to flip a coin, and if it's heads, you can leave. If not, you have to stay. And you keep going until eventually you leave. Of course, you could be very unlucky and be stuck there for a long time. But anyway, in this situation, in 1 minute, the amount of change really depends on how many people you have in the room. For example, if there were 6 people in the room to start with, at the end of a minute, everybody flip a coin, then most likely we would have 3 people left in the room, right? But if we had twice as many people, so if we had 12 people in the room, then after 1 minute we would have lost, instead of losing just 3 people, we would have lost 6 people. The more people you have, the more loss you have. So if y is the number of students left in the room, then dy dt, the change in that, is going to be some constant times the number of students that you have. So as a model for this situation, we have this differential equation, dy dt equals ry. Now, by separation of variables, we've solved this problem already. We know that the solution is that y of t is equal to y naught e to the rt. So although this is a discrete situation, so that we would see, we start with our 6 people, and then after a minute, then we'd have fewer, maybe about 3, right? And then we'd have, on average, 1.5, and so on. So we have this discrete situation. We could actually model this using a continuous function. So we know that if you wait 1 minute, so when t is 1, you'll have roughly half of what you started with. So it's y naught e to whatever the appropriate value of r should be. If you wait 1 minute, you should have about half of what you started with. So if I divide out the y naught, because it's on both sides, I have 1/2 equals e to the r times 1. If I take the natural log of both sides, the natural log of 1/2 is the natural log of e to the r, which is just r. So the constant here should be the natural log of 1/2. So we could say, well, the number of students left in the class t minutes after we start playing this game should be roughly the initial number of students times e to the natural log of 1/2 times the time t in minutes. Now notice, since 1/2 is a number less than 1, this natural log is negative, so we have an exponential that's decaying over time. So we would see the number of students. Although it's discrete, we have this continuous model that approximates it for that. Now that might seem like kind of a weird experiment, right? It's probably none of you have been in detention in that situation, but there's a real-life situation that works a lot like that. When you have radioactive elements, they have some extra neutrons in their nucleus that they wouldn't normally have in their stable configuration. So they would really rather get rid of some of those extra neutrons so that they can feel normal again. Well, these radioactive atoms are a lot like students in this detention experiment. In order to be able to become normal, they're going to have to throw off some of those extra neutrons, or somehow get rid of a bunch of energy in order to become normal again. And their chances of doing that at any time period are about the same. So that would mean that if you, for each radioactive element, there's a certain amount of time you have to wait, and then half of them will be gone. That's just like our detention experiment, right? They have, in some particular time period, it's like they each get to toss a coin, and so we would see the number of radioactive atoms doing something like, if we wait that same period of time, each time we'd see them halving and then halving and then halving again. Now, of course, if we have a very, very large number of these, then it really is kind of a continuous process, right? We don't have to worry about the noise in the number because we have many, many, many of these radioactive atoms all together. So the point is that the number in any time period, the number that will become stable will be proportional to the amount that you have. The more radioactive elements that you have, the faster they'll be able to become stable. Okay, so that means that dy dt, the change in the number of radioactive elements, will lose some fraction of those. So we have this differential equation, and of course the solution to that differential equation is that the amount you have at any time is the initial amount times e to the RT, where RT is telling you something about how fast are they able to become normal, or what's their chance in the next time period of becoming normal again. Okay, let's look at an example of this. A typical smoke detector uses americium, which has a half-life of 432 years. So if you have 1/5000th of a gram, I guess that's 0.2 micrograms of americium initially, how much will be left in your smoke detector after 15 years? Okay, so we know that our model, because the rate of change is proportional to the amount, then we know that our model is the initial amount times e to the RT. Now, we know the initial amount. We're interested, though, in what is that value of r, and this information about the half-life can help us find it, because if we say that T sub h, the half-life, is 432 years, we know that if we plug in 432 here for the time, the initial amount times e to the 432 times r, is going to turn out to be half of what we started with. So we basically have this equation: half of what we started with is equal to y naught e to the 432r. And we can solve this equation for r because y naught's on both sides, so we can divide it out, and we have this equation that only has r in it. We can take the natural log of both sides, and we'll have that r is the natural log of 1/2 all over 432. Now that we know r, we can answer a question about if we have an initial amount, how much will we have left after a particular period of time. We know the amount we have left is going to be y naught, which is 1 over 5,000, because we had 1/5000th of a gram, times e to the r, which we now know that r is this number. So it's kind of complicated, I'll just write r, but I know that number. And the time we're waiting is 15 years. I'm plugging in 15 for t, and I want to know how much do we have there. So we have 1 over 5,000 times the natural log of 1/2 all over, or e to the natural log of 1/2 all over 432, that's r, times 15. And we can figure out what that number is if we use our calculator. At least we can approximate the answer. So we need to start off with 1/2, so 1 divided by 2, that's 0.5, and take the natural log of that number, and then multiply that times 15, and divide by 432, and take e to that number. So I do e to that number, I get 0.97. 0.97 times 1 over 5,000, I could just divide that by 5,000, and I end up having 1.952 to the negative 4 grams left. So 1.952 to the negative 4. 52 times 10 to the negative 4. That would be 0.0001952 grams. Let's see, just G for grams, huh? So we start off with 1/5000th of a gram. So we started off with let's see, if we multiply top and bottom by 2, we have 0.00 tenths, hundredths, thousandths. So we start off with 0.002 grams. The decay rate is pretty slow, so after 15 years we'll still have 0.001952 grams of that substance.